Okay, I see that you can hear me, so I can start. Thank you very much for the introduction. So my name is Piotr Kruszewski, and as it was mentioned just in a moment, I'm working in the Institute of High Pressure Physics, Polish Academy of Sciences in Warsaw. And today I will try to show you the results about the deep traps in gallium nitride materials studied by DLTS-related techniques. Okay, so first of all, we should, this is, sorry, I have to switch. Okay. Okay, so first, please let me present my outline of the talk. So first, I will tell you a few words about the defects and their consequences and show you some general equations. However, I know most of you probably knows this thing, so I will not come into details, just roughly present you some general things. Then I will try to show you some fundamentals about DLTS-related techniques. I mean, classical DLTS, which is a thermally stimulated technique. Then I will go to high-resolution Laplace DLTS, which is a very powerful technique, and I think that this is a technique which can give you, and offer very nice results. And I would like to advertise a little bit during this talk the results obtained with high-resolution Laplace DLTS. Later, I will show you something what is called deep-level optical spectroscopy. I will just mention about that. This is especially important for wide bandgap materials because this process is optically stimulated. So in the part of the region of the bandgap which cannot be thermally scanned, we can use optical excitation. And finally, I will present you our results obtained for gallium nitride materials, which we grow in UniPress. I mean, in the Institute of High Pressure Physics, which is the name UniPress is the historical name. So mostly I will concentrate on Laplace DLTS results. Okay, so we know that deep levels are the, sorry, here you can see the crystallographic defect types in semiconductors. So we know that there are present some impurities, some point defects like substitutional defects, interstitials, and vacancies, but also there can exist also some extended defects like dislocations and also some complexes in the material. Yeah, so the point is that all of those defects introduce deep traps into the bandgap, and most of people do not like defects, yeah, because they can kill the efficiency of the devices, limit some operation of the devices. Me and probably you like defects very much because we can analyze them with our techniques. So we are pretty happy to see defects in our samples. So as I mentioned, we have in case of gallium nitride, we have the bandgap, which is 3.4 eV. So this is quite large bandgap. And if you have some shallow traps like this ET1, then you can easily analyze it with DLTS or Laplace DLTS because it can be thermally activated. The traps which are located much deeper or close to the midgap, these traps cannot be analyzed with DLTS because they are too deep. And then I will show you how to use optical excitation in this case. So just to remind you that the electron, the carrier capture and emission processes are given by this equation. I will not come into details. I just remind you that the emission rate is equal to the this equation. So we have the capture cross sections, thermal velocity, density of states, and also, of course, the trap distance from the conduction band if we are talking about the electrons in n-type material. And of course, there is the contribution from temperature. All of this is exponential dependent. So this is very important. Similar equations can be obtained for whole processes that can be easily found in any books and papers. Okay, so if we have this kind of equation, because we analyze emission rates in DLTS, we should remember that if we take some assumptions, like given here, so the thermal velocity is proportional to the root square of temperature, the density of state e to the power 3/2, and we assume that the capture cross sections is temperature independent, then we can come from this equation to that one. And this equation is nothing else like the equation which can give us the Arrhenius plot. We can prepare the Arrhenius plot because we have the function of emission rate divided by t square, and this function drawn in the inverse of temperature should give us the data in this manner that we can fit the data with some lines, and the slope is the activation energy which we are looking for, and y-axis can give us the capture cross section. Both those parameters are the defect fingerprints which people and scientists publish in the papers and compare between their research, their works. So these are the fundamental parameters which should be obtained from DLTS. How to prepare our samples for DLTS and DLOS as well. So first of all, we should remember that we need Schottky diodes or PN junctions. This is because we are playing with the voltage in diodes in this way that we fill the traps with carriers, for example, electrons, by applying a more positive pass, the voltage, and we try to emit electrons from the traps when we apply reverse bias. So we are playing with the voltages to fill and to release the carriers from the trap levels, and thus we need to modify it by the voltage. We modify as well the Fermi level in both cases. The diode should have low leakage current. Of course, this resistance should be also reduced as much as possible, because it can also affect the results. And especially important technique is a good signal to noise ratio. This is very important to obtain reliable results with this technique. I'll be something more about this in a moment. In case of deep level optical spectroscopy, we need semi-transparent contacts because we will shine the light into the sample through this contact. So the light should be transmitted through the metal, and this must be as thin as possible. So typically we use 10 nanometers nickel metal for this experiment. Okay, so just to remind you how the DLTS signal is collected in the experiment. So as you remember, we measure the capacitance transients at different temperatures, and we observe how the transient changes in this manner that we define the difference in capacitance in 2 points, T1 and T2. If we subtract the different capacitance in those 2 points, we can imagine we can create the DLTS peak in this way that for slow transients, like here, the difference will be almost zero. If we are working in at very high temperatures where the process is fast, this difference will be also zero. But in some intermediate temperatures, we should observe, of course, some maximum, some peak with a maximum at a special temperature, T max. Yes, and in this way we observe our traps and our signals. So each of such a peak appears at the temperature at which the emission rate is fixed by such a relation over here. Yeah, so each peak on the spectrum is the indication that there is a defect level present in the band. Okay, so now please let me tell something about the Laplace DLTS method. The Laplace DLTS is a high-resolution implementation of DLTS, and this is also a very attractive technique. I think very powerful, but I think not too many people are working with this. However, it's really nice and brings good results with, especially, for example, in nitrides, which I will present you in a moment. So the main features comparing to DLTS is lower sensitivity. So this is the problem in Laplace. However, it offers the high energy resolution, which is even a few milli-electron volt at 100 Kelvin. Here you can see the picture which shows that the peak which is observable in DLTS, in conventional DLTS technique, in reality consists of two different levels. This is silicon, and we have in Laplace DLTS we see that there are two components: G4, which is the gold hydrogen level in silicon, and also you have a gold acceptor, which are separated over here. So Laplace DLTS technique offers you very high resolution. Okay, so how these peaks are obtained? So here you can see the spectral. We have the equation of the Laplace transformation. And in principle, this technique, this is the mathematical routine which calculates from the input data, the output data. Yeah, so what we measure in our Laplace DLTS, these are the capacitance transients, which are the function of time. Yeah, so we measure capacitance, which is function of time. And we would like to find this spectral density function, which gives us this emission rates for time constants. It's up to you. So we transfer the experiment from time domain into frequency domain, solving the inverse of Laplace transformation. And typically, what we measure is, as I said, this is capacitance versus time. This is the signal from typical deep level measured by Laplace DLTS. And after application of the Laplace DLTS technique, you observe, you calculate the emission rates for that decay. If it's mono-exponential, you observe one single peak. If it's two exponentials and the difference in the emission rates is at least, I mean, the ratio between both emission rates is higher than 2, it can be resolved by Laplace DLTS. In DLTS, if the emission rates is not higher than 5 or 6, will always appear as a one broad peak. So this is a big advantage of Laplace DLTS technique, especially at low temperatures. As I said you before, the critical point in Laplace DLTS method is the signal to noise ratio. And here you can see the visualization of such a situation. But first, let's tell me few words about the measurement conditions. So first of all, we need to have very nice fixed temperature without drift. If there is a drift, it cannot be larger than 10 millikelvin over tenths of minutes, because it will change the situation during the experiment. The capacitance is transients are averaged many times. In order to get reliable results, you should repeat your measurements at least 1,000 times. Yes, and this is critical because, as you can see here, the calculations are not giving the same results when the signal to noise ratio is not satisfactory. When the emission rates from the signal differs more than 2, like 3, 4, 5, then these peaks are separated immediately after 10 or 20 averaging. However, if you have very closely spaced deep levels, which emission rates will be similar, as in this case, you can see that we need at least 300 or even 1,000 or 3,000 to separate all of the time constants which are present in the spectrum of the emission rates. So you see that it's really important. If you have two emission rates which differs by a factor of 10, this is nothing for Laplace DLTS. This is, you can average it immediately and obtain. However, if the emission rates are around 2 or 3, and there is a big difference in the amplitudes of both signals, then it's tricky. However, it can be done after many averagings. Okay, so now I will move to the problem of the wide bandgap materials. Yeah, I mentioned at the beginning that in gallium nitride we are working at least with 3.4 EV bandgap. It's even higher for argon or any other materials like gallium oxide, for example. So we know that DLTS technique can detect only the trap levels which are located not deeper than 1 EV from the conduction band or 1 EV above valence band. Most of the bandgap, which is 1.4 EV in gallium nitride, is left not scanned. Yeah, we cannot observe this. Why? Because those traps are too deep, and we could say that they are thermally frozen. Yeah, because as you remember, the emission rate depends exponentially from the distance of the trap from the bands, and also inversely from the temperature. So it's even the situation will be even worse in wider materials like argon or gallium oxide. So how could we analyze deep traps in this part of the bandgap? This can be done with optically stimulated emission process, which is typically known as steady-state photocapacitance or deep-level optical spectroscopy. Here you can see the bands and the slide where I wanted just to present you. These results are from Stephen Ringel group from Ohio State University, which are, I think, the best experts in DLOS in nitrides, and I learned a lot from their papers and publications. And you use in this case light instead of temperature. So deep traps can be emitted from the trap when the light, when the photon energy is in the resonance with the trap level. Yeah, if we apply photon energy, which is exactly the distance from the trap into the conduction band, then the electron can be optically emitted from the trap into the conduction band, and we also will observe the capacitance transient, but this is optical transient, not thermal transient. Yes. So it means that at each energies where the resonance will occur, we should observe increase in capacitance, in measured capacitance. Yeah, when we measure this capacitance transient, and we will take the last point of the transient, we will wait until this transient will stabilize. We should observe the spectrum which should be similar to that. So each of the steps means that at this energy, the electrons or holes are emitted to proper bands. Yes. So this is the way how we could analyze deep traps in wide bandgap materials. This is, of course, very easy to say. However, this process is very complicated, and the analysis is not as straightforward as I show you. But in principle, you could do this. Yeah. Okay. So now I would like to come to our results which we obtained with DLTS and Lapas DLTS technique for NGAN and nitrides. So first, I will remind you or just mention a few words about the material. So we are working with gallium nitride, and gallium nitride is the material which structure is Wurtzite, and with this there are related the interesting effects like spontaneous polarization or piezo polarization. This is very important in nitrides. So if you have material like argon, where argon layers are strained to gallium nitrides, you should expect not only spontaneous polarizations from both materials, but also piezo polarization. This is important and has plenty of applications. The bandgap of gallium nitride is 3.4 at room temperature, very high melting point, which is 1,600 degrees Celsius. And very important is that we have high critical electric field in gallium nitride, which is 300 kilo electron volt per centimeter square. The mobility is pretty high, around 2000. And there is also good thermal conductivity in gallium nitride. And the applications of the nitrides are at least light emitting diodes, which revolutionized the lightning in the world, laser diodes as well, and also high power devices and hence transistors, which are based on this spontaneous polarization effects and two-dimensional electron gas. As you can see here, the gallium nitride and some compounds, by adding the aluminum or indium, you can modify the bandgap of gallium nitride or the compound, and you could observe the emission of light with different colors. Yes, so this is also very important aspect of the gallium nitride based materials. Okay, so let me come to the DLTS to Lapas DLTS result mostly. On the left-hand side, you can see typical DLTS spectrum, which we measure for our NGAN and also for other vendors' material, with two peaks, which one is labeled as E1 and the second is labeled as E3. The origin of E1 is still not clear. However, people believe that this trap level is nitrogen-related defect in gallium nitride. And E3 was also problematic to find the the answer about its origin. However, now we know that E3 is the iron on gallium side defect level. This is the acceptor level, and this is the donor level, which I will show you in a moment more about that. In the middle, you can see how the electric field, which is present in the depletion layer, can affect the emission rates, which we analyze in gallium nitride. In this case, we measured double Laplace DLTS. This means we applied two different pulses, but we kept constant reverse bias. In this manner, you can probe different regions of the depletion layer, and the traps will experience different electric field in these regions. So you can see here very easily that if low electric field is applied, the emission rate is around 150, let's say. But if we have experimental conditions where high electric field is applied, or traps feel the higher electric field, this emission rate increases and the peak shifts to higher emission rates. On the right-hand side, you can see the emission rates shown versus the electric field calculated from these experiments at 3 different temperatures. And you can see that they follow very nicely with the model, 3-dimensional Poole-Frankel effect model. Yeah, so the model where the electric field enhance the emission rate from deep traps. We tried to check 1-dimensional Poole-Frankel effect and also other models, and we didn't succeed. Only 3-dimensional Poole-Frankel effect model let us fit our data nicely with the model. The Poole-Frankel effect model effect appears only for donor type levels. So this is also indication and confirmation that E1 trap level is a donor type level. Similar analysis we performed also for E3 trap level, which is iron on gallium, as I said before. And again, we applied double Laplace DLTS technique with 2 different pulses. And you can see that this effect is not pretty large. There is some shift in the emission rate with the electric field. However, this shift is rather minimal or just very low. And the same, we measured at 3 different temperatures the emission rates and how they change with the electric field, which are shown on this diagram. And we tried Poole-Frankel effect, 1-dimensional, 3-dimensional, other models, but finally we found that phonon-assisted tunneling model is the best which describes our data. And in this model, it's assumed that there is a weak dependence on the electric field, and this also suggests this result that this is most likely the acceptor state, as suggested in the literature. The phonon-assisted tunneling means that you need phonons to excite electron to higher artificial level, and then the carrier is tunneled through the barrier. Yes. So that was a very interesting point which we found last year, and it has a very nice consequence which you should remember. Here you can see the activation energies for those traps, and they are calculated for 3 different conditions, for 3 different electric fields present in the experiment. And you can see that in case of donor type level E1, this difference is pretty high, because for the case where the highest electric field is applied, you see that the activation energy is 0.2. In the case where the electric field is minimal, almost 0, let's say, this gives the activation energy 0.27 almost. So the difference is almost 70 milli electron volts, which is huge. Yes. So you should be careful about this when you do your experiments. In case of E3 level, this is not the case, because as we saw, as I showed you before, this trap is the acceptor level, and it's not sensitive too much to the electric field, and all of the data almost gives the same value. Yeah. So the conclusion which we found from these studies was that the large scattering in activation energies for carrier emission reported in the literature so far can be explained by the electric field influence on emission rates measured by DLTS techniques. Okay, now I just wanted to show you some results on sample which was irradiated with electrons with 1.5 mega electron volts. This is again the same gallium nitride, and you see that we have 3 different doses of the irradiation, and the new peak appears at around 100 Kelvin. This is new peak which we call EE1, and again we applied our double Laplace DLTS technique to see how this changes the emission rates. And the first thing is that you can see that there is not only one peak in Laplace DLTS, but there are at least 2 or even 3. This means that this is not just a single point defect, but rather a complex or some two or 3 defects together. Yeah. However, you can see the main line of the peak, which is over here, and you see again that for low electric field the emission rate is low, and for high electric field the emission is high. So this level is also a donor type level, and we calculated the activation energy for low and for high emission rate, and you can see that in case of high electric field the emission rate is around 94 milli electron volt, while for low electric field this energy is 141. So again, big difference in the calculated activation energy. So you should be very careful reporting the results. Okay, what more? We also calculated the production rate. It means the parameter which says you how many electrons are needed to create defect in the material. So the production rate is defined here as a trap concentration divided by the incident fluence. So we calculated our kilograys which is absorbed dose into exposure fluence, and we calculated the production rates, which are similar in some cases with other reported in the literature. However, this is the only paper dealing with the gallium nitride, which is grown on ammono-GaN substrate. This is a special type of GaN substrate grown in ammonothermal method. Okay, so concluding this part about the gallium nitride, I just shown that the electric field strongly enhances the electron emission rates for deep levels in GaN, that phonon-assisted tunneling process describes the electron emission from E3 level, that 3-dimensional Purfrenkel effect describes electron emission from E1, and 1-dimensional Purfrenkel describes the emission from EE1, this irradiated trap level. Both both traps, E1 and E1 are donors, and that the large scattering in activation energies reported in the literature can be explained by the influence of the electric field. Okay, so now I will present you our recent results, which we got which we published just 1 week or 2 weeks ago about the dilute algon, and this is especially important because it shows the powerful of Laplace DLTS technique. Please look. Okay, so in this study we analyzed argon samples with 2.5 aluminum content and 5%. So DLTS for the set of sample pure GaN, which is red, blue is 2.5 and 5% is a black curve, you see two things. First is that all peaks shifts to higher temperatures, which is of course normal because in argon samples the band gap is larger than in gallium nitride, so that the troughs must be deeper. Second thing, which is very important, is that the full width at half maximum of those peaks, I mean E3 level and also E1, increases. It seems that the peak is broader in 2.5 and 7% samples, and also we observe the broadening in case of E1 for 2.5 and 5%. Here is a very small peak, however, the full width at half maximum is much larger than in these two cases. The activation energies obtained from Arrhenius plots give us 588 milli electron volts, 607 milli, and 634 for those samples. So you see the difference that the trap is much farther from the conduction band. Okay, so now let's look on the Laplace DLTS results. These results over here were obtained for iron on gallium acceptor level, so this E3 level at high temperature. For pure GaN, you have just one line. In case of 2.5 aluminum sample, you see the broadening also in Laplace DLTS, and new peak appears. The same for 5% sample, and additionally, the peak shifts into the lower emission rates because the trap is deeper, so the emission rate is lower in the same temperature comparing to gallium nitride. The signal-to-noise ratio is around 1000 in this case. But if we increase the temperature from 340 to 355, the process, the emission will be faster. So everything should shift into the higher temperatures. And we could do more averagings now because in the same time period, the transient is faster and we can average many times more. So if we have signal-to-noise ratio, which is 5000, you can see that for 5% sample, the peak which appeared here as a one broad peak splits into two components. Two components, yes? We have 3 peaks now. And I will show you in a moment that this peak is not new peak, is not related to new defect level. This is the effect of alloying. What is the alloying? Is the fluctuation of aluminum atoms around the defect level. Yeah. So what I put here is that 0 aluminum line, 0, 1, 0, 1, and 2. What means? This means that this is the component which originates from the situation where you have 0 aluminum in the second nearest neighbor. This is 1 aluminum in the second nearest neighbor, and this for 2 aluminum in the second nearest neighbor. How to explain this effect? Yeah? Here is the 3-dimensional view of the structure, and we see different atoms. Here is the flat diagram, just to see it's much easier to understand. So we have 12 atoms in the second nearest neighbor, and depending on the number of atoms, of aluminum atoms in this region, will affect on the emission seen by Laplace DLTS. So you can distinguish the situation where 2 aluminum atoms are present in the second nearest neighbor, 1 aluminum or 0 aluminum. Yeah? And we calculated the theoretical values, how many aluminum atoms, what is the probability of finding given a number of aluminum atoms in the second nearest neighbor, and you can see that theoretical values are in very good agreement with the experimental data. Experimental data, I mean the amplitudes taken from Laplace DLTS. If you divide the amplitude, for example, for this peak through the total amplitude of the signal, you will get the probability of finding that 2 aluminiums are present in the second nearest neighbors. Yeah? So in case of 2.5% sample, this agreement maybe is not perfect. However, if we increase the number of aluminium in the sample, now we have 5%, you see that the experimental results start to agree very well with the theoretical calculations. So this shows you that with Laplace DLTS, for example, you can see fluctuations of aluminium atoms in the material, because this information tells you that you have random distribution of iron in the material. Yeah, this is very, very important, and we published these results in Applied Physics Letters last week. Moreover, we found that the level, if we recalculate Laplace DLTS spectra into energy scale, we can observe that there is linear shift of the main line of the signal. Yes, so this 0 aluminium peak. Yes, so we can expect that if we add 7%, for example, aluminium to gallium nitride, then we will see that the peak should appear around here. So the splitting should shift around 75 or 70 milli electron volt. This is also very, very nice results. Okay, I will not repeat this because I see that my time is slowly coming. So just 2 last slides. Yeah. Here is the deep level optical spectroscopy, our initial results, because I have a project where I have to build the system for optical excitation, the DLOS, and we did it. There are, of course, some issues also related with this technique and this hardware, but it's in a good point now, and we will succeed, I'm sure. So you can see this steady state photocapacitance, and you see that there are at least 3 points where the capacitance changes. Yeah, there is abrupt increase in capacitance, and this is related to the trap level, which is located around 1.7 from EC, 2.7 and 3.2 in this case. On the right hand side, you can see the optical capture cross sections, which can give you more details about the optical processes measured by this technique. Because here in SSPC you can not easily get the exact position of the level. In case of optical capture cross sections, this can be done because you fit some theoretical models, and from these models you can obtain the position of the trap levels. In this case, we use only Lusowski model, which is the simplest possible case where there is no lattice relaxation in the material, and the deep trap level has a delta type potential. And you see that there is quite good agreement with the data, but more sophisticated models should be used in this case to describe better these results. And we are working with this. And final slide is shown here, just to present you our laboratory. So we have the system for deep level optical spectroscopy over here. So we have light source, monochromator. Here are some shutters, lenses, and so on. Cryostat with optical access. We have Buntons, capacitance meters. We have also lock-in amplifier with impedance analyzer from Zurich, which we use, and of course a turbo pump station and so on. So thank you very much for your attention, and all of those results which I presented you have been published in our papers. Yeah, so you can find more details about that result. Thank you very much.